Okay, are you ready to go, Matt? I'll just
Yeah,
introduce you. You ready?
I'm all
Okay.
good.
All right, thanks very much, everyone. Okay, our first speaker for this session is going to be Matt Wilson. He'll tell us about polycategories of supermaps on monoidal categories.
Great. Okay, thanks. I assume everyone can hear me unless I hear otherwise. Yeah, great. Okay. Yeah, thanks very much for the introduction. Thanks very much to the organizers of ACT for putting on the conference. And also, I'm really thankful that we have a chance to talk about this. This has been a lot of fun. So it'll be really nice to have a chance to share it. Okay, so looking at the title, or even not looking at the title, this is a talk about a paper on supermaps. So I will need to say in kind of some more detail at some point what supermaps are, but just before we kind of jump in, the basic idea of supermaps is that they are the kinds of transformations in quantum theory that can be applied to other transformations that seem a bit abstract, and we'll draw some pictures, of course, at some point. And some of the key ideas here are that in quantum information theory, they let us kind of study protocols that involve devices as resources. Something I've kind of been more involved in is that they, in foundational physics, kind of stretch our understanding of causality and compositionality in physics. So, okay, that all sounds like cool stuff. Before we properly get going, something that kind of maybe slightly sets the scene of why this might be interesting to the ACT community is just to point out that if you look at a lot of papers in the last couple of decades of quantum foundations, or certain parts of quantum foundations and quantum information theory, and you look at papers in applied category theory, you start seeing a common theme amongst a lot of papers. And that common theme is essentially the notion of some kind of a hole, and typically the kind of hole you might be able to insert a process into. So this talk is going to be mainly about these things called supermaps, for which maybe the first intuitive picture drawn was this one on the top left here. And the idea of this picture here is it's quite explicitly a black box. You can't really see under the hood here. You just know that this is the kind of thing that you can insert a process F and a process G into and get something valid in some sense. We'll talk more about that later. These kinds of mathematical objects, originally called supermaps, were also axiomatized in another way and called process matrices. So that's the second picture here, also in quantum foundations. Here, the idea was to kind of imagine the most general kind of space-time environment into which little quantum laboratories can be embedded. Turns out to be the same mathematical object. Very cool. But okay, maybe getting more concrete. In quantum information theory, yet again, there's another place where you can see diagrams with holes being studied. So in this setting at the bottom, the idea is to study non-Markovian quantum processes. And again, authors here were led to the notion of a kind of circuit diagram of a hole. They may be more familiar to this community. Things like pro-functor optics are typically used to model kind of concrete circuit diagrams with holes. And for instance, used to study, let's see, so lenses, and there's a completely non-exhaustive list, of course, there's loads and loads of things you can find, but I just snipped a few pictures from what I could find. There's here some model of escrows, I believe. And here we even had a talk at ACT about causal models and string diagrams. And if you look at the appendix of this paper, you'll find discussion of split node causal models, which are again, these little kind of circuit diagrams with holes. So it's kind of interesting. There's kind of a common emergent theme here of talking about diagrams with holes in. In ACT, they tend to be more concrete the way they're built, but they are typically on more general classes of monoidal categories. The black box stuff is more domain specific. It's about kind of quantum-like theories. But from that more domain specific setting, what gets studied is a kind of more black box notion, more abstract notion of what kind of thing a hole can be. So maybe there's something to be done here, putting all this together. And that's one way of thinking about what we're doing here. But okay, let's kind of jump into the meat of the talk now. So I'm going to tell you about supermaps, these kind of black box holes. And to understand the idea of a supermap, I think that what you really need to understand basically is just the way in which normal quantum transformations were originally defined. Quite intuitively, a transformation is something that happens to states. And so it's reasonable to say a good transformation is one that takes states of my system to new states of my system. But something really important in quantum information theory, at the core of how transformations are defined, is to define transformations to be the kinds of linear maps which not only send states to states, but can be applied to part of a shared state with the rest of the world, agnostic as to how big the rest of the world is. It can be applied to part of a shared state and produce a new reasonable state again. So it's this way of being able to apply something locally and reasonably. And this is the idea of quantum supermaps too, is just that the thing that you're acting on is a bit more abstract. So in quantum supermaps, the idea is to study the kinds of things, the kinds of linear maps, which when acted on locally on a quantum channel, produce a new quantum channel. And that's the basic idea. Now, I said right at the start that these things kind of stretch our understanding of causality and of compositionality in quantum theory. And so then you'll be very disappointed to find out that there's a very nice theorem that says that these supermaps are actually quite simple. So there's a cool theorem that says that each of these one input supermaps always decomposes as a circuit diagram. So in particular, in the quantum channel case, where what we put in here are the deterministic quantum operations, then it decomposes as just some other deterministic quantum operation before and some other deterministic quantum operation afterwards. So far, this is just a normal picture. We've seen lots of pictures like this before. But the interesting stuff happens when you start looking at the multiple input setting. So here we have a picture with a couple of holes in it. And the idea is we can plug a process into each hole. And more specifically, we can plug part of a process into each hole in analogy with the one input case. Now, these are the kinds of mathematical objects that go beyond circuit diagrams with holes, at least in a naive sense. So indeed, there are examples of kind of black box holes like this, or supermaps, which aren't a circuit diagram with a couple of holes punctured. But instead, there are some canonical examples that go beyond this, which are of interest in the foundations community. For instance, you could flip a coin, and if the coin says heads, then you put region 2 or hole 2 after hole 1. So let's say I have time going up the page here. Or if you flip tails, I guess this is a biased coin, then you could have hole 1 come after hole 2. Altogether then, if you don't know the outcome of the coin flip, you have a kind of indefinite causal structure. You have both orders at once. Now, the kind of thing like this that really captured the imagination, I guess, of some of the quantum foundations community is not thinking about kind of classical coin flips, but quantum coin flips. You could imagine using a qubit to decide what order the holes should be in. These things are called quantum switches. There are some arguments, some motivations that these kinds of things might arise in toy theories of quantum gravity. And if we did have them, then there's a lot we could do. They would kind of change, in some sense, how we think about some certain computation and information processing protocols in quantum information theory. So here's just like a kind of chaotic scattering of some papers. There's a much wider class of papers on these kinds of ideas, seeing what you could do better, what you could compute better, or how much more efficiently you could process information if you could make use of these kinds of quantum causal structures. Okay, so definitely we can kind of start stretching our understanding and start thinking of interesting ideas if we look at supermaps, but it goes beyond what we've talked about so far. You can come up with many input processes where some agents' choices in some of the holes determine the orders of the other agents. This is beyond these quantum switches. You can go even further. You can write down things called, for instance, this Lugano process or this OCB process. And these things are so kind of non-causal that they can be used to violate a kind of causal inequality. This is a kind of inequality that mimics the idea of a Bell inequality, which you can use to kind of verify non-locality. Here you can verify a kind of extreme form of non-causality by violation of these causal inequalities. So there's quite a rich class of things that you can study if you begin with the Supermap framework. So that's great. And that's why we're interested in Supermaps. But if we go back and be a bit more explicit about how supermaps are defined, we're going to find what we at least viewed in this paper as a bit of a problem with our understanding of supermaps. So current definitions of quantum supermaps, or supermaps a bit more generally, typically use some combinations of assuming some notion of linearity, maybe some notion of compatibility with probabilistic structure, typically some notion of a Troy-Jamelkowski isomorphism, or maybe more in a more familiar sense in this field, some kind of notion of inclusion into a sufficiently well-behaved compact closed category. So these are the kinds of tools that we currently use to define quantum supermaps. And that's fine, it works for finite dimensional quantum theory, but there are some problems with this. So if we go back to the kind of motivating picture of, say, a two-input supermap, and we ask ourselves, what kind of structure do I need to understand or know about, say in category theory, to understand this intuitive idea of a black box with some holes in it? And I would say at least that basically you need to understand that these purple boxes come from some theory of processes with many inputs and many outputs. In other words, they come from something like some kind of a monoidal category. So something that is kind of odd is that if we think back to our definition methods for supermaps, they reference all sorts of other structure. So at the moment, we don't know how to define supermaps on monoidal categories. And so that's kind of odd, given the kind of intuition that the picture has of the structure that seems to be at play here. So it suggests to some extent that maybe we don't understand supermaps fully. But okay, this is kind of a philosophical or aesthetic point, but it comes with technical problems. So for instance, the exact notion in which, for instance, separable Hilbert spaces, so infinite but countable Hilbert spaces embed into a compact closed category, or general Hilbert spaces, is at least less clear, involves some non-standard analysis and some kind of weak notions of monoidal functor. As a result, it's kind of unclear what the right notion of supermap is on general Hilbert spaces. This is a problem because one of the motivations for thinking about these things comes from quantum gravity, which often comes with things from quantum field theory, which often involves infinite dimensional Hilbert spaces. So currently there's just a technical problem there in combining the two fields. There's a whole framework for physical theories like classical and quantum theory called operational probabilistic theories. If we could define supermaps there, then we'd know how to, then we'd have a kind of handle where we could start asking about stronger than quantum causal structures. But again, we don't have this right now. And like finally, and this is definitely more speculative, it's kind of a question, I guess, but like I see the black box whole kind of picture in quantum foundations, but not in ACT. So I guess a question is whether there could be any use for the black box picture in other areas or other domains in which kind of people from ACT are interested. And maybe a formalization would help kind of motivate to look for those anyway. So there's some technical problems and some aesthetic problems here. And the solution, it seems like it should be a categorical one. Really, what we're asking for here is some kind of good construction for supermaps on symmetric monoidal categories. Now, I've been very cheeky here, and I've inserted this symmetric part, and that is definitely something that is a bit of a problem that we can definitely talk about later. But that's going to be our goal. We're just going to work with symmetric monoidal categories. So our goal is to find a good construction. This, in some sense, would contribute towards solving this problem. I need to say what good is. because I'm giving the talk. Luckily, I get to choose the rules of the game here. And of course, we can discuss afterwards if you agree with these rules. But we essentially have two heuristics in mind. So we say, first of all, there's a kind of domain-specific problem, which is if we have a construction which sends any symmetric monoidal category to a proposed theory of supermaps on it. I mean, it can't just be anything. It can't just send everything to the empty set. This is obviously a bad construction. So what would a good one be? Well, first of all, we should recover the domain-specific definitions that we already have from the physics community. So my construction should be such that if you give me the quantum channels, then what my construction spits out is what physicists would have defined, the quantum superchannels. And similarly, and more crucially actually for this tool, if you give me the symmetric monoidal category of unitaries, then my construction should spit out what physicists would have wanted, the kind of quantum superunitaries. Okay, so that's a domain-specific requirement. But then there's a kind of more domain-independent requirement, which is about asking what kinds of properties we should expect a theory of supermaps to have in general. And we should ask that our construction always exhibits those properties. So there's two things we landed on here. But to even talk about them, we first need to just say a very general thing, which is, it seems like at the very least, we should be able to think of this picture here, for instance, of a supermap as something that has a couple of inputs. And so we should be able to draw it in some kind of categorical structure as something that has a couple of inputs. And then this thing here is like the process you would get out after inserting things in. So this kind of pair here should be a kind of output of our morphism. So we haven't said where this morphism lives yet, what kind of categorical structure it's part of, but we can say some bare minimum things. So for instance, we'd like to see polycategorical structure. What we mean by that is, let's imagine we have a supermap T, which has two kind of input-output pairs for an output. So here's one of them, and here's the other one. We would like to be able to take one of those input-output pairs and plug them into the whole of any other supermap, which is indeed the picture we've drawn here. So indeed, at this kind of more formal level, we expect to be able to contract our morphisms along a wire. So that's good. That's a kind of composition, and it means we're essentially asking for something like a polycategory at least. Okay, you might wonder why we're not asking for more, and we'll come back to that. And we'll come back to that after talking about enrichment. So something else that seems very reasonable is that there are some basic notions of supermap you'd always expect to see in your theory. Just like you'd always expect to see an identity process in a symmetric monoidal category. In a theory of supermaps, it seems reasonable to expect, at the very least, that you should always just have a supermap that just plugs stuff together. It takes F and G and just does G composed with F. Now, the idea that in this theory of supermaps, there is something that does sequential composition essentially means that the theory of supermaps should be a place into which the underlying monoidal category is enriched. Indeed, we'd expect to also be able to take two processes and just put them next to each other, which would be the monoidal part of enrichment too. So, okay, it's actually this idea of enrichment that kind of forces our hand on polycategorical structure, which is kind of cool. So intuitively, the idea of polycategorical structure is that you can compose along one wire, but you can't compose along more than one wire at one time. And the reason why enrichment kind of forces our hand here is, at least intuitively, and this is an intuitive argument, we would imagine that if the morphisms of this theory are supermaps, the states of this theory are probably just the processes, the morphisms from our underlying monoidal category. And then we'd expect to be able to draw, for instance, the swap process as a state like this. And then we can imagine the two halves of the swap process. Let's say one half here, which would be like this input-output pair here. We have another half of it here, is like this input-output pair here. And if we could compose along many wires at once, we should be able to form this formal diagram on the right-hand side, which would lead to this actually pathological, intuitive picture on the left-hand side. In this picture on the left-hand side, if we actually assume the supermap we're acting on is we're using is the sequential composition supermap, then combining all of these ideas together, you would at least intuitively end up producing something like a time loop, which for us would be pathological, and we need to avoid it. And so that's why we're quite strict about only going up to polycategorical structure here. So we have these heuristics, we have some things to aim for. We want domain-specific reconstructions and these general compositional features always. Now, there are some approaches to using category theory to study supermaps in various kinds of domains. So it's worth mentioning there's a kind of higher order causal category approach. And here the idea is to, from the start, assume that you embed into some kind of nicely behaved compact closed category. And then from that, you get a lot of power. You can define supermaps. You can also define supermaps and even higher order stuff. This gives you a lot of power, but of course, it's more domain specific than we're asking for in this talk. Then there's a kind of pro-functor optics approach, which, as we mentioned before, is quite general. It works for any symmetric monoidal category, but what it returns is typically going to be not black box. It's just a concrete circuit diagram of a hole in it. So as a result, we instead focused on something that we had put together previously along with Alex Kissinger. That's paper here, where we defined a bare minimum set of axioms for supermaps called the local applicability axioms. And if you've ever seen the definition of a trace monoidal category, then the axioms will probably look familiar. So the basic idea here was to say, of the basic idea of local applicability, which we're going to build on to do our construction, was to say, at the very least, the picture of a supermap says that we should be able to say what happens when S is applied to part of any bipartite process. This was the key idea that we began with. That means that you have, at the very least, a kind of family of functions that can be applied to processes, and the family is parameterized by this X and X prime, which just declares what the environment is. We need one for each possible environment that there could be. We can write these functions diagrammatically just by wrapping a box around the process that this function acts on. And then we draw some dotted wires just to express intuitively that it should be as if our functions only act on the left-hand side, as in this intuitive picture. Now, the cool thing is that you can enforce this idea of locality, of only acting on the left, by some simple equations. You don't need any more structure to write down these equations. You can write it down algebraically, or you could write it down diagrammatically. Either way, the idea is locality, or only acting on the left, means commuting with any stuff that happens on the environment. So that's local applicability. And it's quite easy to generalize it to a multi-input setting, which is the most interesting setting for supermaps. And a really nice result here is that if you apply this bare minimum axiom, local applicability, to quantum channels, you get back what physicists would have defined in that particular domain, the quantum superchannels. However, this bare minimum axiom of local applicability is not quite enough for the purposes of this talk. It doesn't give us polycategorical structure, and it doesn't recover the unitary supermaps. So let's talk a bit about why that is and how that's solved. It turns out the solution to both problems is the same, which is great news. So essentially, there are locally applicable transformations on the symmetric monoidal category of unitaries, which are like conditional linear functions. So if some property of my process holds, I do one thing. If else, I do some other thing. And because of this conditionality, it essentially can't be extended to a linear map. And so absolutely won't be a physicist's definition supermap. The second problem, which is again a result of these conditional functions, is that for polycategorical structure, if you read it, boil it down, you should be able to give kind of unambiguous meaning to a picture like this. By unambiguous meaning, I mean that in some sense, I could interpret this picture as being one thing applied on the left, and then another thing later applied on the right, or one thing applied on the right, and then another thing later applied on the left. I'd want a kind of interchange law for my model of these pictures to make sense. And that's secretly what's going on in kind of polycategoryness. But it turns out that these conditional functions do not satisfy these requirements. They just don't interchange. In some sense, they're kind of pre-monoidal rather than monoidal. Okay, so these conditional functions are the same culprits for both problems, and that's actually great news. So we can define what it means to be strongly local. So a strongly locally applicable transformation, which at a real stretch we managed to make in as an acronym SLOT, which we thought was nice, is the kind of thing that is so local that it doesn't just apply with like circuit stuff on the environment, but it commutes with other locally applicable transformations on the environment. So for instance, I can imagine S here is going to be my slot. S I can apply on the left-hand side and then apply some locally applicable transformation on the right. If S is a slot, that should be the same as just doing S after having applied my locally applicable transformation T on the environment. So it commutes even with all locally applicable transformations. This essentially forces the polycategory stuff, although of course it takes a while to actually prove, but also some really, really good news is that this solves the unitary problem as well. So first of all, there's the multi-input setting to deal with, which you can just get from the slot definition inductively by saying a multi-input supermap is like the kind of thing that when you fit in one of the holes, what remains is still a valid supermap. So you can do things inductively to define what we call polyslots, so many input slots. And then the great news is this satisfies our goals. First of all, there's the domain independent thing, compositionality. For any symmetric monoidal category C, the polyslots form a symmetric polycategory, and all of the monoidal structure of C is enriched in the polyslots of C. Secondly, there's a reconstruction theorem, the domain-specific stuff, both in the kind of quantum information theory setting and now in the pure quantum theory setting. And that was the kind of extra thing we needed to prove. The polyslots recover the physicist's definition of a supermap. So this is nice. We have a kind of working definition of supermap on symmetric monoidal categories now. And it satisfies all of our requirements. That's this kind of top list. And now, I mean, we have a concrete definition. So a natural thing to try and do is actually to bring this back now to the quantum foundations community and use this to study kind of post-quantum causal structures and supermaps in infinite dimensions. Those are some key applications, hopefully. Then there are some more challenges in actually developing the category theory of supermaps. We'd like to see supermaps, these kinds of iterated things, the kind of things that can be applied to other supermaps. We'd like to be able to have tensor products and representability if we can. And there's a sense in which it's not obviously and probably not very canonical, this construction. So it would be really cool to see kind of nicer categorical constructions, ones that in some sense functorial or universal. Probably to phrase what it means to be universal, we need a good definition of theory of supermaps and structure preserving maps between them, which means there's a kind of broader challenge of defining a kind of just categorical framework for theories of supermaps in general. So that's all I wanted to say. So thanks very much for listening. Here is the paper that this talk was based on if you're interested. And yeah, I'd really love to hear any questions.
Okay, thanks, Matt. Okay, yeah, we've got 2 minutes for questions. Are there any questions in the room or online? Yeah. One in the room.
Thanks for the nice work and the talk as well. I'm not very familiar with polycategories. I kind of understand your requirement for avoiding loops, but I was wondering if you could say a bit more how the two connect, like this requirement for having polycategory with the requirement to avoid loops. And why is that the solution?
So it's okay. Let's see if we can go back to the picture. Yeah. So I guess what I want to say here, it's a little opaque to me still. Exactly what the connection is, for instance, between like this kind of loop and this kind of time loop. It's not entirely clear. But I don't think I can say much more than I said here, in the sense that we just have this basic idea that maybe more broadly, you shouldn't be able to connect along more than one wire at a time, because it would let you kind of construct pictures like this, where, because supermaps can do kind of weird signaling tricks, if you're not careful and you allow any process to come in here, again, you can kind of create these time loops. I think I'm probably just saying what I said before, so I'm not sure how useful that is.
Okay, I think perhaps we're out of time there. Let's thank Matt one more time. Yeah, thanks again, Matt. That was super clear.